as a recap, what ended up happening last week is we went through things like these pulleys, which we called Atwood's machines. And on these pulleys, we said that we've got two forces of gravity opposed to each other, and that the tension ties them together. Okay? In the big picture, the whole system, we're worried about force of gravity of 2 versus force of gravity of 1. In the subsystem, we're worried about tension. And to find tension, you would only look at the subsystem. These trolley problems will be about the same, where we actually have to look at the subsystem to be able to find the tension. But then we also said that we've got a couple of things going on here. That if we draw a free body diagram, that we need gravity. This one has gravity as well, but it's on a table. So what opposes that gravity? The fact that the table gets in its way, so there's a normal force. And we don't have to worry about box 1 pushing up or down. We only really have to worry about box 2 pulling the system. So when I look at the whole big picture, there's only one force that exerts anything outside of the box, and that's because this is imbalanced. The force of gravity box 2 is imbalanced by the gravity of the planet outside the system. So we said F equals ma. That's worth points. And then we also have that the net force, well, the only thing acting on it is the force of gravity of box 2. So when I worry about F equals ma, how many boxes does this force of gravity have to move? Just this one? Or does it also move the other one? It moves both of them, yeah. So M1 plus M2 times A, that's the net force, equals M2G. Yeah. There you go. Good. Do we know enough to just plug it in? I think so. A equals M2 over M1 plus M2 times gravity. And so we have A equals 2 over 3 plus 2 times 9.8. Two-fifths of 9.8 is about 4/10 of 10. So yeah, 3.92. Is that the decimal? Meters per second squared. So we have the first part. We have part A, the acceleration. So the tension. The tension is on which box? Correct. I heard somebody say box 1, and I heard somebody say box 2. The tension's on both of them. Which one do you want to solve first? I'm going to go ahead and pre-select box 2 because it's harder. So if you picked box 1, you picked the correct answer. Let's see the hard work then first. I'm redrawing the diagram, which is right up above it. So we've got the force of gravity. Net force equals ma. But what two forces am I worried about? The net force equals the force of gravity of box 2 versus tension. Okay. All right. So if we have the force of gravity of box 2, if all we're looking at is box 2, that's the net force of box 2. So all this really is ma. You know, let's rearrange it first. Tension equals Fg2 minus the net force. So tension also, you could say, is equal to M2G minus M2A. And if you're like me, probably not, You're going to factor first. Most of you are willing to plug it into here. The mass is what number? 2. G is 9.8. A is what we just saw for 3.92. So I'm going to say 2 times 9.8 minus 3.92 because I'm probably going to do it in mental math form. And 10 minus 4 is about 6. So 2 times 6 is about 12. So this is about 11.76. What is that? That's the tension. So what units? Newtons. And then we said it was easier to look at box 1. What forces are we worried about on box 1? Right. The net force in the x direction on box 1 is equal to the tension. That allows, this little x right here allows us to ignore the up and down because we know they're going to cancel, right? And so I write it like this just so I can explain clearly that all I'm worried about is how it's getting pulled forward. And there's no friction holding it back. And so if that net force is the tension, that force is also equal to MA in the x direction. And so tension equals MA, and we know that the mass of the top box is 3. And the acceleration is 3.92. So 3 times 4-ish, about 12-ish. It's probably 11.76 newtons. Right. It should be the same, yeah. That makes sense. They're the equal and opposite force. I would call it T1 versus T1. I didn't even say anything about tension 2 because it's the same tension. All right, number 4. Number 4, we've got a mass of 100 grams. What am I going to write in this box with M1 if I wanted to express 100 grams? 0.1 kilograms, 0.2 kilograms, and 0.2 kilograms as well? Okay. What's my net force equation? MA? Cool. Just so you know that this is the fact that the net force is going to be equal to M1 plus M2 plus M3 times the acceleration. All 3 boxes are going to move, right? That's all we're saying. That this net force will end up moving all 3 masses, that they're tied together, and that we have to use, be able to move those. What else is the net force equal to? Yeah, what I'm really asking is what's outside the system, because if I'm asking how the system will move, that gravity reaches outside the system, and that gravity reaches outside the system. So Fg, wait, what did you say? I'm going to call it 3 because that's M3. Fg3 minus Fg1. Okay, because this one ends up going down, this one ends up going up. So this one, while it's going down, is positive. And this one, because that gravity is opposing that motion, I have Fg1 minus Fg1. So using this equation, I'm going to break it down into the net force equals M3G minus M1G. That's what I'm going to substitute in. And also I know that that net force equals,
All the masses combined multiplied by acceleration.
yeah, M1 plus M2 plus M3 times A equals M3G minus M1G. And so I'm going to divide everything by M1 plus M2 plus M3. And we start to realize that if we took the time to memorize this Atwood's equation right here, that we're going to have to build our equation anyway, because anytime I throw a table at you, that will change things. This is a different equation just based on the fact that we do have our opposing forces, right? Having to pull all three masses now. So we've got the net forces acting on our total mass. I like to factor the top. So I've got 0.2 minus 0.1 times 9.8 divided by 0.2 plus 0.2 plus 0.1. So I've got 0.1 divided by 0.5, so that's 1/5 of 9.8. Or 2/10 of 10-ish. 1.96 is what I ended up with. 1.96 what? Meters per second squared. I used a lot of space just to get the acceleration. To find the tension in the two strings, I would look at M3's diagram and M1's diagram. And that this is moving down with gravity. Let me see. If I just had this box going down and up, I know my force equals MA. And I know that my net force is also equal to
Gravity minus tension.
yes, gravity minus tension. Gravity is 2 times 9.8. MA is 2 times 1.96. 0.2 times 1.96. FG is 0.2 times 9.8 minus tension. We're looking for tension. All right. Is this tension going to be equal? No. Is it going to be more or less than this tension?
Less, greater, more tension.
I would say that it's actually less, because this one's pulling forward and it has to pull hard enough to move both of those two. But that's yours to find out. So find out what the equation on this side is. The opposite, that it's moving up, so it's tension minus force of gravity is how it will move. But you'll figure that out too. Okay, I'm gonna let you do number 4 on your own. I just want to finish up the notes. I'm gonna skip number 5 because it's relatively the same as number 3. Let's look at the back and answer these. If the force on an object increases, the acceleration of the object also increases. If the mass of a system decreases, the acceleration of the system increases. If I reduce the mass, the acceleration can increase with the same amount of force provided. And then looking at this graph, what does the slope show? Slope equals change in y over change in x. And then what's on the y-axis? Force. And what's on the x-axis? Acceleration. So you said that the slope is equal to the mass. So what's the mass of this object? I think it goes all the way up to 60 in 10 seconds. Yep, I got 60 over 10, so that's 6 kilograms.